All right. Hey everyone, welcome to my stream. So tonight's going to be a bit shorter than usual, just because I'm a bit tired and I want to go to bed a bit earlier tonight. So looking at it, maybe about 2 hours. It's 9 o'clock here, so I want to stop around 11 o'clock. So last week, yeah, it was last week, I was working on the emulator and got to a point here. Let me open up Visual Studio here. Got to a point where I started rendering lines. I was implementing the vector display logic from the VIA chip, and yeah, I got a bit stuck near the end. Let me just bring this up. Hey, ABDCW, how's it going? Need a little coffee. Hopefully wakes me up. So yeah, this is the code I was working in just last week. Oh yeah. Nice little goto. I think I haven't written a goto in years. Hey, it's not staying here there, this is just me messing around. But yeah, the reason I got stuck was actually quite interesting. I was following this one document here called internal.txt, which goes about and tries to explain how the vector display works, and it's actually quite good, you know, like it gives a pretty decent understanding. I like how it has this cool analogy of how the vector display, like the analog stuff, works. The analogy here is like household plumbing, and it talks about having water pressure and all that. That's pretty good. However, it's not complete. Basically, this document is missing some important bits. Like, for example, one of the questions I had last week when I was looking at this was, you know, how does it when it starts drawing, I believe it was related to ramp. Like when the ramp is enabled, basically when it's pulled low and it's enabled, how does it get set back to disabled? And I think when I asked that question, I was looking here at this BIOS routine here, and what was I looking at? Let me see here. No, that's not it. Let me see. Okay, so that's port B. So that's it. See this bit here for the ramp. What was I was searching for? I was searching for some code here in the BIOS that would turn it off, and I didn't find anything that would turn it off. And I had actually surmised that maybe what was missing here was something like, I actually think I said this, like the shift register. There is a shift register in one of these, and I was thinking maybe, where is it? Maybe the shift register actually has something to do with it, where it shifts out a bit into the ramp or something. Turns out I wasn't completely far off from the final solution. So I haven't spent much time since last stream, but I did do a little bit of reading. I found this actually, I'll go to the table of contents. So there's this nice documentation written by some Chris Sallow, I believe. Can't really find exactly who it is, but anyway, this document is this little HTML documentation here. Kind of goes through and explains very nicely how to program for the Vectrex, and it has some interesting bits in here. Like it's got this section on the timing, which is really useful actually. One of the things I learned from reading this here, it says like Vectrex uses a 68A09 microprocessor at 1.5 megahertz, and as he explains, he says one cycle basically is 1 out of 1.5 megahertz, right? And in order to have a 50 hertz stable display, which is most desirable, I guess, on this system, we must do everything we want within a limit of 30,000 cycles. So basically what that's saying is that the way the Vectrex generally works is that you have about 30,000 cycles to do all your logic and display before the beam needs to be reset back to 0, and so that things remain stable. So he says here the BIOS uses timer 2. So there are 2 timers in the Vectrex. Timer 2 is used to keep track of system time. And there's this function in the BIOS called wait recal. This routine waits for that timer to expire before continuing and recalibrating the vector system. So this BIOS timing information can be set at BIOS RAM location Vectrefresh. So there's actually a location here in memory that has this value of 30,000 in there. In fact, what it is it's a pointer. So he says here it's a word pointer. He says here, CA3D, yeah, is the word pointer. CA3D is the timer low byte, and CA3E is the timer high byte. Thus, a value of 30,000, 7530 would be stored, 7530 in hex, would be stored to the BIOS RAM location with a sequence like load this, store D. So actually, I wouldn't be surprised if we saw exactly this kind of thing in the BIOS here, or something like it. Vectrefresh. Oh, sorry, in the BIOS, I said. 3075. Here. So see, this is init. This is the beginning, init OS RAM. Like, it's really the very beginning, early on. We get inside here, and it says, like, init the refresh time to 7530 in hex. So that's written load D, and then store D to CA3D, just as he says here. And he says that he actually tried playing around with this, but that in the end, any value stored in there ends up kind of making the screen shake. So basically, don't mess around with that. So that basically says that, like, you do your logic for, let's say, for your screen, for your game, and then at one point you call this function, right? And you're hoping that you're doing this always within your 30,000 cycles, so that you have a nice smooth 50 hertz. Because if you like miss that threshold, like if you run for over 30,000 cycles and then call the Vectrefresh, you basically are going to lose that frame, right? So then you end up with like 25 hertz instead. So if you're consistently missing that frame. Yeah, so, and the other thing he says is, he says the second timer, so timer 1, is used for drawing vectors within BIOS vector drawing routines. Now, we actually saw a little bit of this last stream, and this like shed some light on that detail. He says, actually, while drawing vectors, the timer is set with the scale factor, right? This is very confusing, but he's saying that the name scale here, this is kind of like has a dual meaning, because scale and the timer value here are both exactly the same thing, because it's how long does the vector beam draw for, which is effectively a way of thinking about it as a way to scale the vectors. He says it here. He says, which is the low byte of timer 1, a VIA register. So this D004. Thus, scaling directly relates to timing. Using a large scale factor always takes a lot of time. If at all possible, use small scaling values. And then he says, see also the next vector's length section. So we will actually go to that section. But actually, just before I do that, let me just take note here. I wanted to take some notes because I've been kind of reading a lot, but not actually writing a lot of stuff. I just want to like write a little note here for timing. So basically, I want to say that timer 1 is used as system time. Oh, sorry, no, timer 2 is used as system time. I will say that wait recal, That's what it was called, yeah. Wait root cal waits until timer 2 reaches 0, then resets to value stored in, I'll say, resets to 16-byte value stored at, here we go. And yeah, and in fact, it's in inverse order. This is the low byte and this is the high byte. Then resets the value stored there, which is by default set to 30,000. It is exact. It is 30,000, right? Yeah. Which is set to, so actually that also tells me that this timer basically, which makes sense there, that this timer decrements every cycle, right? Just wrap that. Okay. 60 by that, which, okay, that's good. So that's timing. Timer 1 is used for drawing, and I'm going to write a bit more about that as we keep reading. No, not this. So yeah, so the next section here, I think it was vectors. There was some stuff in here that was also illuminating in terms of how it works. So here, very interesting. So we're going to talk a little bit about all the things we can set when we're drawing, right? So we looked a bit at this. We saw brightness. There are two ways to control brightness. First, the intensity, which is a value from 0 to 7f. So that's interesting, right? Because basically it means from 0 to 128, not the 0 to 255. And he says if the seventh bit is set, there is no intensity. So anything above 128, the value is going to be 0, right? So another way to think about this is the intensity is a signed value. So if we go into the negatives, it's basically 0. 0 means black, 7f means full brightness. Apart from the intensity, you can vary brightness of vectors by drawing vectors more than once for dots, leaving the vector beam for a longer period of time on the same dot. So this is the idea that, you know, when the beam writes its value to the phosphors on the screen, if it continues to write there, the phosphor will get brighter over time, right? So that's something that definitely would like to emulate, because if you do play on a Vectrex, you can see very clearly that there are like dots that are brighter, whereas like let's say a line is drawn, it's a bit brighter at the beginning and then not as bright for the length of the line. And that's, you know, I assume it has something to do with that. For the last, there is a bias variable, vec.dwell, CA28, which sets a counter for how long the vector beam will illuminate the dot. So I actually saw this last stream as well. I was wondering about this vec.dwell. I was curious here. Dot dwell time, yeah. And it's like referenced somewhere in here. Yeah, so there are these dot functions. Like if you want to draw a dot specifically, it's going to just draw at one specific XY location for some amount of time that's determined by what's written in vec.dwell. Now I don't care too much about that, but what I do care about are some of these details. So let's write this down. Go back to our notes here. So I'll say brightness, value from 0 to 128, which is 7f. If greater than 128, it's 0. So black. Okay, so that's good. Positions. The positions of vectors are most of the time relative to the last known position. Sometimes the position is not interesting when drawing a vector since it was set some other time, and now drawing just continues. Positioning with any function is done in relation to the present scaling factor, and then here you go, he says time. You can see once again, these two are one thing. The programmer must keep track of the position and should zero it now and then. If the set position is not used within a certain time, the position will drift. And he says here, this is kind of interesting, he says, my Vectrex drifts always to positive, positive, so he means in the upper right, towards the upper right. And he says a few centimeters per 10,000 cycles. Now, if you think that every frame you have 30,000 cycles, that means that, you know, if you're not re-zeroing it often enough, like even re-zeroing it only 3 times per frame would not be good enough. You know, in 10,000 cycles, it will have drifted a few centimeters. So that's pretty bad, right? So this basically tells me that you have to do this kind of zeroing pretty much, like I would say probably you draw an object, like a closed object, and then you want to zero and then draw the next closed object and then zero. Assuming that these objects are relatively small, made up of, you know, not too many vectors. Okay, position is given in values from -128 to 127. So here we're talking about the x and y values that we feed to to the BIOS functions, which then eventually make its way to the hardware. So I'm just going to write here positions, values from -128 to 127. Now, length of vector scale. So here we talk about this kind of important detail. The length of vectors here means something like the speed with which the beam will travel across the screen. The scaling is something like the time for how long the traveling will be done. Thus, it is easy to see that traveling with a speed of 10 for a time of 5, which would equal a traveled space of 50, is about the same as traveling with a speed of 50 for a time of 1, which also results in space of 50 to be covered. The only difference is that the first will take 5 times as long as the second. Length is given in values from -128 to 127. Most length information is set with first y and then x length. So, okay, actually, yeah, right. So that's it. When we're talking about positions, we mean positions on, like absolute positions on screen, because we're dealing with a 256 by 256 display, right? And now we're talking about the length, vector length, or scale. And what he's saying is that similarly, right, we set values set from -128 to 127. ABDCW asks, random question, is C at all acceptable, so to speak, for writing an emulator, or is C++ preferable? You can use whatever language you want. Lots of people have written lots of emulators in C. In fact, pretty much the early emulators, like back in like 98, 99, when I was playing with emulators, not writing them, but just playing with them on my computers, they were written in C with some inline assembly. I prefer C++ just because there are features of C++ that I enjoy, I like using, but C is absolutely usable and often used even to write emulators. Okay, so yeah, what I wanted to write here, yeah, so he's not talking about how to set the so-called speed here. He's just talking about how to set the length of the vectors, right? But that like makes part of the way it works. So I'm going to say here vector length, right? And I'll say these are the x, y values that are set. Y first, then x. And actually the reason for y first and then x, I'm gonna show you why that's the case. It's something else I learned. Let's go back here. What was the other thing I saw that was really interesting? Yeah, it's here. So all of this is really interesting, but I think the scaling part was interesting. I'm not going to actually show you the code, but he says the above program also sets the scaling value to 50, which is still a pretty small scaling value. The Vectrex achieves scaling with a timer, right? So this is the timer 1. The time for how long a vector is drawn or just positioned is the scale value. Thus, as also mentioned before, using high scale factors results in a waste of time, right? Scaling factor is set by loading the value directly to the timer of the VIA 6522 chip, namely this register here. And it says below you can find some functions that will set the value. Actually, there is no functions here below, but let me take note of this here. So this is vector length, and then here we're going to say vector. Okay, let's just kind of do this in 2 parts, right? We're going to say x and y. Like what they are, these are he calls them, I've seen that like this value be called velocity, speed, strength. Let's say strength, you know, or speed or something. And I'll say from 1 Okay. Set y first, then x. And then here we're going to say scale, which is also time. And set via timer 1. Maybe I should use via. set in timer 1, which is basically this, the via T1 counter low, which is a 1 byte, right? And one thing I do wonder is, I think yeah, so this must, he doesn't mention it here, but I assume that this value from 0 to 255, right? Because it's a timer, it's a single byte countdown timer, it counts down to 0. And yeah, so I'm gonna see, I'll have to confirm this. And actually if I go back here, if there's anything interesting here. A lot of this is like stuff that I've already said. Okay. Okay, nothing interesting here. I mean, there's a lot interesting, but nothing that I want to call out. So here you talk. Okay, so here actually I think is where we start to see scaling. Because in the previous one, he basically is drawing hello world, you know, to the screen, like what you see here. And then in the next one, he says, let's now change the size of the text. And in fact, he says that you just have to change some variables in memory that it uses to figure out the text and all that. And he says, as mentioned above, the height is a negative size, the default size. No, okay. What these numbers actually are is the speed of the vector beam as described in length of vector scale. That's interesting because he says -8 here. The default size, which is -8 and 72. So yeah, so I'm not quite sure what that means. If these really are the so-called speed of the vector beam, what does a -8 value mean? Here loads F1 minus 14. Yes, so I'm not quite sure. All right, so that's that's why I have a question mark here. You know, like, can these be set negative, and what does that even mean? There are quite a few positioning functions available, some absolute, some relative, and some reset functions. So here he kind of shows the move to functions. These are actually some functions we were looking at last stream. Okay, line drawing. Talks about all, this is interesting too, he talks a lot about all the kinds of things that you can do with drawing, right? He talks about, you know, if you want to draw only one vector or a list of vectors. These are like what the BIOS routines provide for you. You can use functions that draw just a single one, or you can call one that can be given a list of vectors to draw. You can include positioning information or no positioning information. I think what that means is like absolute positioning as opposed to relative positioning. Including scaling information, excluding scaling information, including brightness information, excluding brightness. So like basically if you have like a list of vectors, do you want in that list to also specify position, scale, brightness, or mode? And here he says mode has to do with patterns and other stuff. So I think you could draw like stippled lines and stuff like that from what I remember. So for more information, so there's a long list of the BIOS functions. He actually has an example here where he does like a move to, and then he does, actually there's a lot of stuff here that's interesting as well. Yeah, that's it. It's not like, the thing is that this is a bit too high level for what I need, right? These are just calling BIOS functions, but understanding what the BIOS functions do and then looking at what like their code helps us to understand how to implement the emulator. So it is important to understand this code. So all he's doing is he's loading 0, 0 for both the X and Y. Then he's calling move to D. So it moves there. He sets the intensity here to 5F, which is like not the highest. 7F is the highest. And then clear vector miscellaneous count. In order for drawing only one vector, this must be set to 0. So this I believe is like this is a piece of the memory area that's used to set how many vectors you're going to draw, and it's not actually the count. It's like the count minus 1. So think of it as the upper limit for your, you know, less than or equal to in the loop. So in fact, what it does is that the function will draw. It'll assume there's at least 1, and then it'll decrement it, and as soon as it's negative, it stops. So that's why if you have to draw one vector, this needs to be 0. If you're drawing 2 vectors, it needs to be 1. And then here we want to move to y100 x50, and then we say draw a line. So it'll draw a line from 0, 0 to 50, 100. And then it repeats. So anything I want to point out here? He says the beam internally is drawn for a fixed amount of time, the scale value, in the direction specified by the y-x position. So this is interesting, right? Like basically I said it moves to 50, 100. The truth is it moves to 50, 100 on a grid that depends on the current scale factor. That's the way to think about it, right? If you kind of like imagine, you know, like if you can see this, like a grid. This grid basically will shrink or grow based on the scale factor. And that's what, the X and Y here. And one of the thoughts I had was that perhaps I'm doing it wrong. In my code here, I'm actually trying to implement drawing of lines. Where is it? Yeah, like I have a feeling that what I'm doing here is not necessary. Like I'm taking into account the formulas from internal.txt that show like how to, how the beam really moves over time based on voltages and all that to draw its lines. But I think that since I'm writing an emulator, I don't really need to do this. If I understand what the scale is right now and what the XY positionings you want are, I can just stop there and do line drawing based on that information. I don't need to actually emulate the way the beam moves. Like I don't have to compute the kind of stuff that happens, I think, at the hardware level with the beam itself. So this is just some ideas that are bouncing around in my head right now, trying to figure that out. So yeah, interesting stuff here. So he says register A stores the Y position and register B the X position. These positions are the translated strength of the vector. The beam internally is drawn for a fixed amount of time, the scale value, in the direction specified by the YX position. The position is internally translated to a voltage with which the electron beam is deflected from the center of the tube. And that's the part that I'm saying is, what I'm emulating here, and I'm not sure I need to worry as much about this kind of voltage translation, as much as all I need to do is say, hey, I know this information, I know what the hardware wants to do with it, I just need to draw the lines, right? Okay. So, okay. Yeah, he talks about weight recal earlier on and says it does something strange at the end of this function. So weight recal is that one you want to call once every frame within your 30,000 cycles. He says that at the end it calls this function called reset0ref, another BIOS function, which does this here. And this is important. It will go ahead and set B here to via control, and so what it'll do, it'll set blank low and 0 low. And as he says here, he says that means that both blank and 0 are enabled, right? So let's just take a note of that because this is something that's important. All right, so weight recal calls what's it called, reset0ref, which enables both blank and 0. Sets to 0, both blank and 0, right? So what does that mean? This means that the vector beam is always on center, 0. This is true until the via control is modified so that the 0 flag is high again. So basically when the 0 is enabled, it is always writing zeros to the X and Y, effectively. So that brings the beam back to 0, right? But while it's in that, while the 0 is pulled low and it's enabled like that, you can't actually write any values to it. It needs to be pulled high to stop it from zeroing. And he says the simple draw line D function does not do this. Move to D does, however. So this is kind of like one of those, you better understand this, right? Because if you wanted to draw from 0, 0, like after resetting and you put yourself at 0, 0 and immediately wanted to do a draw line to somewhere, it would actually not draw. In fact, it would keep the beam at 0, 0, and you have to know this. There's like this implicit contract or understanding that says like, Well, usually when you move to 0, 0, you know, when you reset, you know, after your weight recal, like the most likely thing you're going to do is a move to. So then the move to goes ahead and disables that zeroing, and then you're good to go. Which is kind of crap, really, if you think about it. But I guess, you know, they wanted to save that those. I guess they wanted to be careful and not put that kind of disabling of 0 in every single function. Or maybe they thought, you know, you need to know this, but for your convenience, for certain functions like move to, we went ahead and did it for you. But it's kind of one of those you need to know type of things in this API. So you can instead use move to function, call also insert the following 2 lines. So here, okay, so then he says here you go, you can also do this, which will make sure that blank is low, so that we draw. I know that we. What's this? Just wondering why he would put blank low actually if we want to draw. Because here he's saying, you know, we can go ahead and make sure 0 is high, so we disable the zeroing, but he keeps the blank low, which would be bad because then you wouldn't draw. So I think he meant actually to say blank high. And in fact, this is what I was searching for last week. I was looking for, I'd found in the code, CE, in the BIOS here. Yeah. I'd found places in the code where this happens, right? Like blank low, 0 high. There it is in the move to that we were just talking about. But like nowhere is the blank set back to high explicitly. See here, blank low, 0 low. This is what I was looking at last time and was surprised, right? It's like blank low, 0 low. Everywhere I search for via control, and there are very few instances of it, you know? Here we have one where we in move to where we store blank low. Here we have another one in reset 0f where we store blank low. And then reset 0 int, which also stores blank low, right? So I was like, hey, well, if blank is always set to low, which means we're not drawing, how does it ever get set to high again? When, you know, if blank is not set explicitly to high anywhere, how does this work, right? Turns out it's related to the shift register. So we'll get to that soon. So let me just take a couple of notes here. Only the move functions will disable 0, set to 1, or you have to do it yourself. I'm going to write blank zero enabled. When enabled, overrides like no vector is drawn, beam is off. I'm going to say 0, also 0 enabled. When enabled, sets moves beam to 0, 0, center, screen. All right. Here he actually shows how to use a vector list. So let's see this code a little bit. Okay, yeah, so he does this thing here where he basically has his turtle line list, right? He says there are 23 It's actually 24 vectors to draw, but he has to put -1, right? Because as we said, that's what you need to tell it. And then he goes ahead and he puts like these offsets in X and Y. And then what he does is this little trick where to make, you know, to statically make it bigger or smaller, he can go and set the sprite blow up, he calls it. It's really just a scale. So it's a good old, you know, turtle line vector list centered around its own origin. And then this is a scale value, which he sets to 25. So, and then when it compiles or when it gets assembled, these values will be multiplied and it will have the correct value in there. So this will be 50, for example, 50-50. So that makes sense, right? And so he goes here, main will loop forever. Does the weight recal. He sets a scaling factor of 80 to A. So let's see here. Move to time 1 low, this means scaling. So I don't know why he says 80 here because it's actually 10. I guess it's just a mistake. So he says put the scaling factor there and then store that into our timer here, right? So that's our timer, right? So that's how long it'll draw lines. And then actually, one question I have here is this how long it'll draw each vector? And I think it is. My assumption is that it's going to. We'll take a look. Actually, I'm assuming that when we call, where's the draw? Yeah, when we call this draw VLC function, that it'll take that timing value and use it for every vector. So it'll take this 10 in hex. That'll be interesting to see. I guess that's like 16 decimal. Okay. Move to D. Move the vector beam to the relative position. Set the intensity. So yeah, so we move to where we want to go. So 0, 0. And then we go ahead and say load the address into X of the turtle line list and draw the line now and repeat. So this here, draw VLC. I don't think it's actually, is it called draw VLC in here? Draw. Yeah, okay, it is that. There are a few here. Draw VLC. This routine draws vectors between the sets of YX points pointed to by the X register. The number of vectors to draw is specified as the first byte in the vector list. The current scale factor is used. The current scale factor. The vector list has the following format. Store B. So here's the timer that he sets to 0, right? Then we wait for it to into timeout. Go back for more points. So yeah, this is the timing logic that I'm trying to understand here. It's a bit surprising. Oh no, this is the counter high, not the counter low. He's zeroing out the counter highs. Okay, so that's it. That's not... I guess that what it's saying before, it was saying it uses the current scale factor, meaning whatever was written into timer low. Right? Let's just go back to the browser here. Yeah, see, this is counter low, to which you wrote 10. And I think I read this. It's when you write to the counter high, it kind of starts the timer. I think that's what I read. Let me see here. Yeah, you see here is low, which is the scale factor, and high doesn't say that what it is. But I think maybe what's happening is that the value you write into via timer 1, maybe it doesn't get decremented directly in there. You know, maybe it keeps the value you wrote. Then the code says write to here to kind of start this internal timer. And then after that it says it wants to keep checking this one bit to see if the timer finally ran out, right? But after that it doesn't go and reload the timer. So I think that's probably how it works. It's one of those timers that can reset to its original value when it finally reaches 0. That's probably the case. So we're going to need to read a little bit about timers to understand that. Obviously it's crucial to getting the drawing right. So I want to write something about timers here. This timer 1. So the low byte, it contains the actual like countdown value. High byte, I think, is used to start the timer. And I'll write here, I'll write that C drawline D. Drawline D sets this to 0, sets it to 0, 0 per line it needs to draw. Okay, actually just give me 1 second and I'll be right back. Okay, sorry about that. Okay. So yeah, high byte and low byte. I need to learn a bit more about timing, and there is information on that. I saw it when I was reading. So yeah, I think it's very interesting that that we see that, you know, like how important the timing is for all of this. It's how the scaling is done, from what I can tell. And in fact, it's not like, and another thing I was wondering last time, right? I was like, well, you know, I expected that when you enable the drawing, that at one point you'd have to say, okay, stop drawing, right? Like even if you have a timer, but in fact the timer is connected to the ramp, if I remember seeing. So something about the timer being connected to the ramp. I'm going to look that up soon enough. This is obviously crucial, right? If I want to get rendering to work properly, I need to really understand this interplay between all of these things, because that's all what's used in terms of drawing vectors. All right. So he has here some stuff here. Let me just like read through this again. Yeah, he talks about how like actually his, you know, in his code, that long list of vectors are not absolute positions, but all relative positions that you have to kind of compute from absolute positions, and that's what he shows here. So he talks about his little scaling thing. So he says here, the program listed uses a sprite blowup of 25 and then scale factor of 10 hex. Uses per update round exactly 3158 cycles. So he's talking about how many cycles it actually takes to draw his turtle. And then he says, this is where it's interesting, right? He says, if we change the scale factor to 50, so we move it up, and we set the sprite blowup to 5, which gives us an object of exactly the same size, we need already 4,705 cycles. Right? So what he's saying is, if we make it take longer to draw, right? We set our you know, sprite scale or vector scale lower and say take longer to draw, so we get an equivalence, right? Exactly, yeah. So basically 25 times 10 is 250, if you look at it that way. Same here, 50 times 5, and he says, which gives us an object exactly the same size. It says this here takes 4,705 cycles instead of 3,158, which goes to his point about, you know, make your time smaller, your scale smaller, and use bigger numbers. It says this does not look like much, but keep in mind that with just one object you will not be able to create great programs, and that you will also want a pretty fast round below 30,000 cycles to have a steady image. So yeah, you know, just drawing this one turtle took up a 10, was it? Pretty large factor, right? Yeah, like 10%. It's crazy. Note, there are also vector list routines which have a mode or pattern byte. With these routines, you're able to draw invisible lines, therefore objects are possible that are not drawn in one go. There are also functions that provide collision detections. This is interesting, right? There are functions that provide collision detection of vector lists, and there are functions with which you can rotate and scale your vectors as needs arise. I find it really fascinating that there's actually collision detection stuff for these lists of vectors. Okay, so I skipped the sound playing and joystick stuff, and then here we get to vector display, and I think this is where where I think a lot of the information we want is going to be described. ABCW says, good night, I'm gonna go finish studying C. Good luck in the emulator. Thanks, man. Appreciate it. So, I'm not gonna read all of it. He mentions internals.txt by Keith Wilkins. So, yeah. So here he talks about the three bits that we are already reading and using, 0 and blank, which I just wrote about, and then the ramp, which I haven't written much about. Let me just take note here of so blank is via CB2. 0 is CA2. I mean, we already know this, but just for completion. And let's talk about ramp here. So the ramp is PB7. And I think ramp actually is the opposite. I think it's 1 enabled. Now here's our via timer 1. It's a one-shot mode timer, meaning that it counts down once and then it stops, from what I understand. We'll see. And here's the interesting part. You see PB7 enabled. This here is connected to the ramp. And that's what I was saying earlier, that when you want to start drawing, you set up your X, your Y, your brightness and all that, and then you set your timer 1 and you kind of say go, right? You turn on the timer, and then what that does is it connects to the ramp, which turns on the drawing, and then I think when it's done, turns it off. So it's directly driven by the ramp, which is really interesting, right? And we'll read more about it below. PB7 enabled. Or is it the other way around? Does it mean that it gets enabled by the ramp? We'll see. We'll see. There are shift register modes. So this too is important. It says shifts out under T2 control. Yeah, what is this again? Yes. If I recall, this shift register is basically used to determine what the line is going to look like. Like if it's all ones, if the whole, let's say there's 8 ones in there, it's going to draw a solid line. And the way it works is that timer 2, which is the system clock, if I recall, every 2 cycles it'll do a shift, and it's a circular shift, right? So it'll shift bit 7 into bit 0 every 2 cycles. And what that means is that if you want a stippled line, like a line with a different pattern, you can write that pattern into your shift register, and it'll use that. And since it's shifting out into a circle like that, it'll keep that pattern going. Now, and the other part of this is how the shift register is also connected to, is it the ramp? No, it's not the ramp, right? Because the ramp is moving. I think it's connected to blank. Yeah, I think that's what the shift register is also connected to blank, so that when there's a 0 that reads out of bit 7, that is connected to the blank, which means stop drawing or draw, whichever it is. I think it's inverse connected. So like if it is 0, it'll actually set the blank to 1, which means don't draw, and then if it's 1, it'll set it to 0. So we'll double check on that. Let me write my hypotheses here, and then we'll double check them. See, I wrote it here, connected to ramp. That was timer 1. So it is connected to the ramp. We'll see a bit more about how that works. And shift register. So let's write about the shift register. Why does he call it mode 4? I don't know. And what I want to write about the shift register is 8 bits used to set the pattern of the line to draw. I'll say bit 0 shifts into bit 7 every 2 cycles of T2. And I'll say bit 0, when bit 0 shifts out, it also sets blank to inverse value. Okay, so let's see if I'm right. There are via interrupts, via auxiliary control register, and the via control register, we know what those are. Then the integrators, which are the things that are used to move the beam and driven by the ramp. Now, if the above mentioned don't tell you anything, you're probably better off learning a bit more. So these do tell me something, so I guess we can keep learning. We can keep reading. First, I'll describe how the bias position the beam. So let's see here. So he says here the bias sets up a bunch of stuff for you, so that's good. He says the bias initializes the data direction registers of via port A, all for output, and port B, all for output. So this is something I saw like a few streams ago when I was reading here about the via chip, and one of the things it talks about in here is how like you can set port A and port B. Each bit can be programmed for what direction it moves in. Like, do we write to it? Do we read from it? And at first I thought, okay, that's interesting, but I think I had said it, not sure we need to care that much. And I was right, because it's set up once and never really changed again, because the Vectrex is not, you know, it's not like general purpose, right? You don't get to decide how it works. It wants to use the via chip specifically for the Vectrex. So what it says, go back to my browser. So what it's saying is that port A is all for output, meaning we only write to port A, and that's the one that goes to the DAC and to the X register. And port B, all for output except bit 5 and 6, which are input. It's not here, but port B, 5 and 6, if I recall, I don't recall, but here. Comparator input, see the value, the word input here, and external device initialized to input. So these are the only 2 bits that are set to input. One of them is for the comparator, which I'm not quite sure yet what it is, and I'm not sure either what this is, but it just says external device slot pin 35. So maybe we'll learn eventually what those are, but these are the only 2 bits that are read out of port B. Otherwise, all of these are written to only from the CPU. All right. Just give me a sec. Okay. So yeah, so this comes back to the via auxiliary control. It says the BIOS initializes the data direction. Yeah, it then pokes 98 to the via auxiliary control, which sets it up this way here. So bit 7 says T1 enables PB7 output, which, if I recall, means enable PB7, and PB7, as we just saw, is the ramp. Enable PB7 output. Okay. 6 one shot, 0 T2 one shot. So by setting these to 0, it's saying that these timers are not one-shot timers. So this kind of means, if I understand correctly, it means that these timers will reset back to to whatever value was initially written in them. So they kind of remember the timer value and it resets to that timer value. So that goes with my hypothesis for how it must work for vector drawing for the vector list, that as soon as it reaches, and when it's done drawing one vector, it resets and then start maybe counting or maybe waiting for you to now start the timer again by writing into the high. One thing I'm wondering here is like, what I'm wondering here is, what I'm gonna do is I need to, like, I'm gonna write my code assuming it's a non-one-shot timer, but I'm gonna make sure that these values, these bits are never changed after they're written to 0. Like they should never be set to 1, because if they are, then I'd have to correctly make these timers one shot. But I'd be really surprised, because that would kind of break the way the BIOS works. So I'd be extremely surprised if any game did that. But maybe there's some games that bypass the BIOS and decide to do their own thing. So if I want to emulate that correctly, I kind of need to support it that way, right? So I'm going to take a note of that as well. Where do I want to write this? I'll do this. BIOS sets we will assume timers are not one shot, but assert that these never get set, that these bits never are set to 1. Okay. These bits, shift register control, 110. Yes, this means shift register control 110 says to output to CB2 under control of phase 2 clock. So what this is saying is that for the shift register, we want it to output its high bit, low bit. I'm not sure. I'm going to double check. I was thinking high bit because I'm thinking left shift, right? So it outputs to CB2 under control of phase 2 clock, which I think means every second tick, right? Every second cycle. Bit shifts every 2 cycles. That's what I wrote here. I don't know if it's bit 0 or bit 7. Yeah, see, I'm really not sure. But it is interesting to note that that's what this means. Basically, I should make sure that none of this gets set to other than 98 in general, because it doesn't seem like that would be the case. Actually, let me read this here. There are mainly 2 aspects of interest in that setting. First, a shift mode, which is shift mode 4, which means that shifting is enabled by poking something to the shift register. Which means that shifting is enabled by poking something to the shift register. And that the bit shifted out from bit 7 is circulated back to bit 0. So actually I got this wrong. Bit 7 shifts into bit 0. Shifting continues even after 8 shifts. Shifting is done at half the system clock speed. I think that's why they mean phase 2 here. The bit that is shifted out is put into CB2 blank. Blank is 0 active. That means that if the bit is 0, output is switched off. See, that doesn't make any sense, that line. Blank is 0 active. No, actually it does make sense. Blank is 0 active. Oh, right. It's like double inverse, right? We set 0 to enable the disabling of drawing, right? So then that means if I come back to what I wrote here, not to the inverse, sets blank to value of that bit. And we'll say here, don't draw, one draw, right? It's basically beam off, beam on. The other interesting bit is the one that enables PB7 output. Okay, so yeah, so this I want to make sure this basically confirms what I remembered reading. And then the next part says the other interesting bit is the one that enables PB7 output here when timer 1 is active. PB7 is the ramp signal, which is 0 active, but becomes inverted. So I think this is the place where it becomes inverted. What it comes to is that the integrators are switched on when the bit PB7 is set. Integrators on means that the vector beam is moving. So let me just go over this again. So T1 enables PB7 output. So while the timer is active, right, it sets the ramp signal to 0. I wonder why, I guess they're saying becomes inverted, meaning that because it's non-zero in the timer, the non-zero-ness is the inverse of that is set on the ramp. Oh, okay. Let me just take a look at that picture. No, not this one. This really not super nice picture, but I think here we're going to see something interesting about the PB7 if I can find it. PB7. 7 would be blank. It's not really easy to read this picture. But what I'm thinking right now is what it means is that the VIA has this PB7, right? And that it's connected to a ramp signal. But when the timer is writing to be PB7, every time the value changes, that the value on PB7 is inverted, which then gets sent to the ramp. So that while the timer is writing a value that is, say, non-zero, let's say 1, that gets set to 0 on the ramp, meaning while the timer is active, ramp is enabled. Okay, so where should I be writing this? I guess it's part of timer 1. Yes, connected to ramp. Basically, while timer 1 is active, non-zero, ramp is active, 0. So drawing, so integration occurs while timer is active. Right. vector beam is moving. Perhaps you can already at this point see where this is leading us. The beam will be positioned for a certain time. The time is stored in timer 1. While timer 1 is active, the beam is moving. Depending on the value in the shift register, we have this or that output. If there is a 0 in the shift register, we have no output at all, since at each shift a 0 will be stored to the blank line, which disables all output. If a 1010 would be stored to the shift register, we would see something like a dotted line. Now, depending on the strength of the vectors, we would see short dots or wider dots. And if all ones was set, we would see a solid line. Following is some part of the BIOS move to function. I thought this was interesting because this is actually the function that I spent like 10 minutes looking at last stream. So basically we store Y. Oh yeah, and that's another thing that I realized is that the order of operations can be surprising, but because it's an analog signal, it doesn't always work the way I think, right? So for example, here we store Y in port A in the DAC, and then we enable the mux. Now, before enabling the mux here, that value that we store will end up in the X register actually. Basically, every write to the DAC will go into the X. Then, not that it really matters because it'll be overwritten, but just something to keep in mind. Then we clear port B, which will have the effect of enabling the mux, right? And then that ends up writing to Y because it'll choose the 0th output, which is Y. Then we say here, save the D register on the stack. Then here we set up blank low 0 high to the control. So what we want to do here is we want to blank low means no draw, and bring our guy to 0. Bring the beam to 0. Now we clear the shift register because it's a move to function, right? We don't want to draw anyway. We disable the mux. Now this is interesting about the order of operations that I was assuming, and I was wrong, and is that you don't need to store X into D8 and then disable the mux. It can be done the other way around, right? Or you could basically invert these two. Although in this case, you have to disable the mux because you don't want to crush the Y value. So you disable the mux, and now from now on, all values written, in fact, the current value that's in there for Y immediately makes its way into X. And then we overwrite that by storing the value we want for X in there. Then here we say clear, timer 1 count high. Again, they don't talk about it, but I think this is what starts the timer. I think by writing something here, it will reset the timer by taking the value that it's supposed to have in timer, like taking the value in timer low, the low part of T1, and saying start counting down from that. And then we bring back D because we actually wrote to it. And then this was that part that I was looking at about taking the absolute value and figuring out some timing. And there was some like, weird logic here about waiting. There's a wait for timer 1 here. So that's like, make sure we reach the place we want to move to. And so he writes here, he says, in D is the YX position. The first thing the function does is send Y strength to port A, which also is input to the DAC. The DAC output can be distributed via mux to different destinations. Since this is the Y coordinate, we enable the mux with mux settings, which send the DAC data to the Y integration data storage. The strength will be added at each cycle to the Y integrators, once additions are allowed. Yeah, and actually that's another interesting thing. He calls it the Y integration data storage, right? This is important because it doesn't go directly to the integrator just yet. The integrator is only going to take values, it's a separate piece of memory if you think about it that way, and it only takes that value once the ramp is enabled. This is just like the target value that we want, the strength. Now the mux settings which enable sending Y, the mux settings which enables Y is 0, 2 bits of via port B. Enabling the mux itself is also a bit of via port B, but 0. So mux is enabled by clearing that bit. Here's a small description. So he goes here and shows what we've already seen many times, all the bits of port B. So we're not going to go through there. Then the function stores register D on the stack, which also serves as a short delay before disabling the mux again. Right after that, we load register A with CE, which is a bit mask, which as a bit mask is this, right? So it's basically blank to low, so disabling output, and 0 to high, which disables zeroing. Oh yeah, that's right. It's actually 0 to high, not to 0. Now if zeroing is enabled, the vector beam cannot be moved since it is grounded. It remains in 0 position. The setting thus allows the vector beam to be moved. Next, we clear the shift register. That means when the integration starts, the vector moves. There will be no output since at every shift out, a 0 will be moved to the blank. So see there we see how important the shift register is actually. Even when we're moving, we need to make sure that it's set to 0 so that it doesn't do any drawing. Because it's going to be writing to the blank line. Last stream I thought that I wasn't looking at shift at all, and I thought, well, you just need to set blank and you're done. But actually blank is driven by shift. And since their shift register is set up to always shift every 2 cycles, it's definitely going to affect blank and therefore must be written to. Integration will start as soon as ramp is 0, which I said before will be negated before reaching the integration circuit. Right. So integration will start as soon as ramp is 0. And then I guess what he's saying is that that has to do with actually, we're going to get there. Okay. After we disable the mux, remember, the enabled bit for that bit was 0 of Viaport B. It gets disabled when the bit is set. This means that the DAC value now only gets to the X integration storage. So that's when this code he's talking about this increment here. This increment here makes the 0 value in port B become 1, which disables the mux because that's bit 0. Alright, then we store the X strength of I port A and thus to the DAC register. The next step is to enable the timer by writing to the high byte. See, that's where I'd seen this. And he says, the high byte is cleared since we integrate at most to FF time. So, you know what I think this means? If I'm reading this right, thinking about the hardware of the timer, I think what this means is there are these 2 bytes, right, for the timer, and it means it's a 16-bit timer. And I remember reading this. It is a 16-bit timer. It can be used to count down from, I suppose, 65,535 down to 0. But it's not done that way. And I think the way it works is that you first write to the low, and then it's waiting for you to write to the high. As soon as you've written both, I think at that moment it starts counting down from that value. Now the way I think it works is that the programmer writes only to the low byte, right? So like the timer is waiting for the high byte to be written so that it can say, okay, now I've got the time you want and I'll start counting down. And what the BIOS does is it clears it. And he says here, since we integrate at most to FF time, meaning we only allow the timer to count down from 255. That's what I'm reading here, which is the highest scale value. And he says the scale value was set before even calling the move function in the low byte of the timer. So that confirms everything that I was thinking about that timer. So let me write here. So I'm going to change this just a little bit. I'm going to say here timer 2. Because I don't think I had a... Oh no, sorry. This is timer 2, which is a system time. Yeah, timer 1. High byte, I think, is used to start the time, yeah. So what I'm going to write here instead is 16-bit timer, where you first write to low byte, then to high byte. Right. Upon writing to high byte, it starts the timer counting down to 0. For Vectrex, programmer game code I'll just write here. For Vectrex, game code writes only to low byte, and BIOS routines will write a 0 to high byte to start the timer. This means timer will contain 0 to FF max. I'll just say contain FF max 255, which is the scale, the max scale value. Which I assume is almost never done, because writing large timer values just makes things render very slowly. But that's what it means. And I'll move this little comment of mine here. I'll say C drawing which sets. Okay, connected to ramp. So I know I'm not doing much coding tonight, but all of this information is crucial. So I probably won't do any programming tonight, but I'll have collected enough information so that next stream, which will be in a couple days, hopefully I'll be able to actually do this properly. And then here I will connect it to ramp. Basically, while timer 1 is active, yeah, so we just looked at that. The next lines, and he writes here, in my honest opinion, not necessary. All this computing of some extra cycles to wait, actually I don't understand it. Since the additional waiting is done after the timer reaches 0, that means that ramp is disabled anyway, so no change to any vector position. So see, this kind of makes me feel better, because last stream, I was stuck for a while trying to understand what is all of this code about, right? I mean, I didn't know about timer 1. I assumed that the timer was used to wait for when the drawing was complete, but all of this code to like compute A plus B, and then, you know, if it's within some less than some range, then we do some extra delay, otherwise we do other delays, you know, all of this stuff here, even this guy who doesn't understand what it's about. So that makes me feel better. Anyway, let us assume that we reached the point marked here. So he has a here in there, here, right there, right? And this piece of code here looks like it's just checking to see if timer 1 has completed. In fact, what he's doing is he's checking bit B. So he's doing an ANDing of what's in B against what's in the interrupt flags here. And bit B has whatever value was stored in there. That was the sum of the absolute values of the two. Okay, so let's see what he says about it. Register B is loaded with 40, which is the bit mask. Oh, so sorry, is it loaded with 40? Oh yeah, it is. Right. And okay, let me just check something. So bit B 40, and he's talking about the via interrupt flags. Here. It's this one here. Yeah. If you write 40, basically we're turning on bit 6. So timer 1 interrupt flag, read T1 count low or write T1 high. So we only read. So read T1 count low. So I guess this bit gets set once the timer has elapsed. It says which is the bitmask for timer 1 interrupt testing. The loop's only purpose is to wait for the time to expire. After the time has gone by, the ramp will be again not active. No integration is done, and position of the beam will not change anymore, presumably, since the ramp is disabled as soon as the timer reaches 0. Why on earth the BIOS programmers wait for some more cycles to go by, I don't understand. Apart from that, you'll see that once you know where to put the correct timers and what registers are used for that, it is sort of understandable how a vector is positioned. So, you know, maybe there were different versions of the hardware, and maybe they wanted to have some extra cycles in there for the beam to really stop moving and get ready for the next move. Who knows? But I do want to take note here. I do need to check again on how the timers work, but I think what I'm reading here is that there's this interrupt flag that needs to be set, and I assume it gets reset as soon as we write again, you know, the two values to low and high. So I'm going to write that here. It's actually for both timers, but anyway. When timer has elapsed, interrupt flag is set. For timer 1, it's it sets bit, was it bit 6, while for timer 2 it sets bit 5. I'm gonna write here, I assume that flag is reset when timer is started again. Okay. The vector drawing routines are essentially the same, apart from the shift register, which is not cleared but set to some value, which when shifted results in blank to be non-active, thus the beam is illuminated. And he says, here's a sample of draw line D. So we send Y, enable mux, point to the next coordinate pair, wait a moment, disable the mux, right? Send the X value to AD. Then we say shift register will get FF, solid line, and timer 1 high gets 0, which means the timer starts, right? Which means that blank will be, no, not blank, sorry, ramp will get enabled. I remember reading somewhere, someone saying that if you really want to emulate the timing properly, when the timer actually takes a couple of cycles to begin. So even when this happens, it still takes 2 more cycles before drawing actually begins. I think I read that somewhere. I'll take a note of that. When timer is started, both bytes written. I think I read that it takes 2 cycles before the countdown begins. Star B, set the T1H scale factor. T1 interrupt. Right, so load into B the 40 to check for T1 interrupt bit, and then we bit B, so we keep checking for it to time out. And then once it's equal, we go to, while it's not equal, I mean we keep jumping back, otherwise we NOP, so we wait a moment, clear the shift register. I wonder why they cleared the shift register. Not necessary, right? Anyway. Yeah, I wonder why they do this. Because in any case, yeah, that seems odd. It seems odd because, like, you know, for every line we need to draw, we're going to set the shift register to FF. So then this only would matter for when we're done, and when we're done it goes to this check 0 ref. Maybe it's for that, I don't know. Anyway, so it does that. Decrement a line count, which was stored in here. And that's it. Alright. Is anything interesting in here? Yeah, so once again, it says, yeah, this is interesting here actually. He says, now we prepare the shift register. We poke FF to it, which means that we will be plotting a solid line. Notice that we are not integrating yet. But the light is already switched on, since shifting starts the moment we set a new shifting value. Oh, okay, that's interesting. Okay, that's what that meant about the shift register. The moment you write a value, it immediately does a shift. And then after that, 2 cycles later, it will shift. So that makes sense, right? Because if you want to like stop the beam, you can write a 0. You know that write will immediately shift the 0, the 7th bit into the, you know, it'll do the shift and it'll also write immediately to blank. So I'm going to write that here. Upon write, shifts shift once immediately, which is useful for disabling beam right away, not 2 cycles later. And so that's why they turn it off here, right? Because once you finish drawing your line, even if you have more, you want to make sure the beam turns off so that it just doesn't stay on for all the time that it takes to do these extra cycles of CPU instructions. Otherwise, you'd get these really thick lines between each one of your vectors. These thick dots between the vectors. But actually what he says here is that he says the light is always switched on a few cycles too early. Yeah, like as if this here should have happened probably, when should it have happened? Well, I guess there's no choice, right? I mean, I guess maybe the pattern could have been written into it before doing the shift. No, sorry. This is setting the shift register. We set shift, we set the timer which starts the drawing, and yeah, basically there's like nothing we can do. The time it takes here for it to complete this instruction, and then even this instruction, it's already, if we turn on the beam, it's already been drawing and writing to the phosphors on the screen for a couple of cycles. And he says here, that means actually drawing, he says, after we clear the high value of the timer, this enables the ramp integration. Now the vector beam is moving. Okay, I thought he was going to say that basically there are these dots that you see, which is the case. There's always this kind of dot at the beginning of every line, and then you draw the line, and then there's another dot for the next one. It says the movement will cease the moment the timer reaches 0. Unfortunately, the light is not switched off automatically. We therefore wait in a loop till we get a message that timer 1 has expired. After that, we switch the light off by clearing the shift register. So that too means that probably there's a couple cycles where it's writing at the, the last pixel. Done. The complete line is drawn now. As you can see, there is no fiddling with any strange additional wait loops while drawing lines, but otherwise it is exactly the same thing as positioning the vectors, apart from the FF in the shift register instead of 00. This sort of confirms my suspicion that these strange loops in the positioning functions are sort of useless. In my experiments, I have not seen any differences if I left them out. Okay, kind of good. So that's as much as I read of this documentation. The other thing that I found this Russian website. Actually, I'll show original. Right? And thanks to the magic of Google Translate, I can actually understand what it means in English, which is really cool. So somebody here, and actually this is great here, you can see the dots at the beginning and ends of each line in this image. See these dots here? So that really goes to show like what we saw before, that drawing a line, because of the way it works with the hardware, the shift register and all that, there's always a few cycles where the beam is on before it starts moving, and then the beam is on even when it stops for a couple cycles before it's switched off. And I think it's here that he mentions it. Oh, I can't actually click on this without it showing up some kind of weird menu. Okay. So what I wanted to show was this picture, this diagram here. I actually was drawing my own diagram, and this is very similar. Basically, what we see here is all the important parts of what we care about in terms of emulating. So there's the VIA chip, right? The CPU can write to it. Basically, you have port A. That's the port A is the one that's directly output its values to the DAC, to the 8-bit DAC here. We also show that doesn't show port B here. Anyway, here you have mux channel select Y or Z. So he's not showing there's actually 4 outputs to the mux, but in relation to drawing, we only care about these 2 here. So the mux can select between Y or Z. So Z is this one here. So the Z is actually directly, it controls the brightness, and it looks like it's connected directly to the circuitry, to the hardware for the beam itself. And you can see here that the interesting part is the blank, how like this concept of the blank that will override that value. So if we enable blank, it's gonna override the value that gets sent here and ignore whatever was set in this register. And it's actually kind of a type of storage. So for Y, and similarly for X, they both have these like little storage values. And here you can see like the mux is used for Y, but the 8-bit DAC has an output to the X, and it's always connected. So no matter what value flows out of here, it always ends up in X, which is why the X value is the last thing we need to write. So one thing that's interesting here is we see this ramp, right? The ramp controls integration. So what I'm understanding here is you can think of it this way. If the ramp is enabled, then these values will end up into the integrators. If the ramp is disabled, these values just stay here, and they don't end up in the integrators. And in here, the zero here is connected directly to the integrators, and these acts as an override again, similar to the blank. So if 0 is enabled, zeros end up into integrators, and the values coming out of here are completely ignored. And then the integrators end up moving the beam in X and Y. So I find that to be a very useful picture, and it kind of confirms a lot of stuff. There is a lot of important information in here that I want to keep reading. I haven't read this page yet. I just saw this diagram. Interesting. Talks about here concerning the meaningless delay instructions. It says after writing to port 6522, the BIOS code sometimes waits for several cycles. Otherwise, the following entry may not pass. When it is necessary and when not, the question is rather vague. Judging by the experiments, both mine and other people, it is not necessary at all. Perhaps this was required for early Vectrex specimens, which is what I assume as well. It says, it should be understood that if you want to draw long continuous vectors, for example the full width of the screen, then this is possible only at the maximum scale value. However, if it is maximal, this automatically means a decrease in resolution, in the sense that a step in unit per vertical will mean a distance of approximately the width of the bright line. That is, there will be a gap between the parallel lines. Right. The width vertical will mean the width of the bright line. If you make long lines of several short, the joints will be visible. If you make long, yeah, obviously there's like some, you know, translation issues here. Just trying to understand what it means. In practice, it makes sense. It makes sense to constantly switch to scale. In one large, the line is drawn. In another small, ray moves to the beginning of the next drawing. Okay. If you draw a long horizontal line on a scale of FF so that it ends at the right edge of the screen and the right end is far behind the screen, you will not be able to move it to the left so that the right... If you draw a long line from minus 128, 127, so top left corner, with a scale of FF, so the maximum scale, so that its left end is at the right edge of the screen by the time it's finished drawing, and the right end is far, the left end is at the right edge of the screen, and the right end is far behind the screen. It's interesting. He's talking about like something about, and I remember reading this also in internal.txt, that like something about saturation, because he says if you kind of like push it beyond the limits of the screen, what's going to happen, right? And he says something like if you try to do that, the movement will to the left will slow down. The movement will slow down and stop before reaching the desired position, about a quarter of the screen. And this is due to the limitations of the maximum amplitude. The emulator, by the way, does not understand this. So he's saying that the whatever emulator he's using doesn't behave in the same way as the hardware in this case. Interesting. I won't worry too much about like that right now, but it would be cool to emulate things exactly the way the hardware does it. But right now I'm really just interested in getting the base case working, like the common case, right? The brightness of the vector is determined not only by the value of z, but also by the time that the beam is in a particular place. Therefore, the brightness will be higher if the ray moves. The honey. B, the beam travels along the same trajectory many times. I wonder what honey is a translation for. I guess he meant beam here, but somehow... Anyway. In this regard, it is worth mentioning about points. They are drawn by simply switching on the beam without integration, waiting in the loop for some time, on which the brightness and turning off of the beam depend. Right. So it looks like this guy wrote some code to actually do what the BIOS normally does. Rather than use a BIOS routine, pattern must be specified exactly after the start of integration so that it is empty before it. Otherwise we get a curved tail at the B, and I don't have the rest. This delay is necessary in the event that the next line should start from the end of this. Without delay, there will be a gap between them unknown to science. I love this. I mean, I think what it means is there will be a gap between them, and the reasons are not really known, you know. But the translation from Russian brings it to it's probably some expression. Unknown to science. Restore the normal management of the beginning of integration by timer. Oh, that's interesting. Because it looks like here he's probably writing to the auxiliary control something else. Here. We cut out the output of BB7 to start the integration manually, instead of starting the timer. Ah, that's interesting. In the previous section, to start the beam movement, we started the timer, which automatically started the integration. And then they waited for the ending, checking in the cycle whether the timer had finished counting. There is another way of drawing the line in which the timer is not used. We start the integration manually by setting the ramp on the foot of PB7, and then by whatever means wait until the beam creeps in the specified X and Y direction. Love this translation. Creeps. Depending on the task, simple, NOP, or a loop in which in particular you can update the value of shift register, if you need a dot and dash line, can be used for waiting. And at the end of drawing, the integration stops, also manually. So what he's saying here is, rather than take advantage of the timer, you can do it yourself and then do cycle counting. Since the timer is not used here, setting a scale does not make sense and does not affect anything. The direction and length of the line are completely determined by the values of X and Y and the delay between the start and end of integration. In the BIOS, this approach without a timer is used to output characters. Ah, that's true. When we were looking at how it prints characters, we didn't see anything with timers. So then that probably means that the VIA auxiliary control is set to different values, and I need to make sure to emulate that. Let's see. If I go to here, there we go, print string, shift reg mode 110, T1 PB7 enabled, timer 1 to PB7 is enabled, so that's 98. But see here we clear, no, store A. What does A get for this part? So yeah, 98 goes in the auxiliary control here. But here we store A. What's the value of A? Oh, it's here. Load D. So A and B. So here instead of 98, we store 18. And then that gets written. So what is it right here? Shift reg mode 110. Timer 1. Shouldn't this mean BPs have been disabled? Let me see. Oh, 11 o'clock. I will be stopping shortly. Just want to check this one detail here. Programmer. So normally 9.8 is written, right? Which is this here. And if we go look at auxiliary control again, 0001. So sorry, read from left to right, 100. (110) is the only mode used by the Vectrex ROM. Am I reading this right? 98 in hex. So 98 means writing 1001 in the high. So sorry, 100 here, and then 110. Oh yeah, sorry, 110 gets written here, here, and here, and then the last two are for these latches here. So 110. Okay. And then 9 and 8, and then what was the other one we saw? 1 and 8. So 000, 110. So it's true that the 110 doesn't change. But here, these ones are affected. In fact, it's really this one that gets affected. Okay, that's really interesting. Basically, the fact that and I need to make sure I emulate this correctly. The fact that when the timer is active, that it writes to BB7 only needs to be done based on whether this is set or not. So it's this one. Connected to ramp, basically what timer was that? Set to integration occurs on only if via control bit 7 is whatever set. Okay. So yeah, I collected a lot of information tonight. So what I think is that I need to implement this logic. I need to implement the way timers work correctly. And I need to also take care of the shift register and make sure that it does the right thing. I need to... And another thing that is evident here is that I need to work with cycles. Like last time I worked here, I added this update function with delta time, which I called to do rendering based on time. I might keep this, I'm not sure, But what I also definitely need is a way to advance the via based on cycles, which means that maybe I can't really have both. We'll see. Yeah, I don't think I want this. What I think I want is really like in my debugger. You see here when we execute an instruction, we get this number of elapsed cycles here. I want to take that and I want to update the via with the number of cycles that have elapsed. And this way, I can do all the things I need to do. I can advance my timers, and I need to draw based on these cycles. And that's still the part that's a bit elusive for me, is figuring out, well, it's not completely, I think the way to do this is to understand how much the beam can move based on the values in the integrators and the timer, and kind of come up with like the most I can move right now is this many pixels or something per cycle. Yeah, like this many units per cycle. And then based on the number of cycles, I take that and I move myself in both X and Y by that amount. So like I need a... Yeah. And I guess what I'll do is I'll make those floating point values, and I'll just, it's kind of like a rise and a run, you know, the delta X and delta Y that I can move right now. And I will integrate, I'll add over time those values. Because I'm thinking different things, like I'm thinking about like, you know, doing my own kind of line drawing, like Brehensen line algorithm kind of thing, so that I know exactly, you know, which pixels to draw, or maybe kind of keep it at a higher level and say, you know, just kind of keep track of the start and end positions. The problem is going to be the stippling effect, right? And there's going to be problems with accuracy. Yeah, I might have to do my own thing. Okay. It's good stuff for me to think about. Hopefully, you know, I'll let my brain chew on this for a couple days. And on Wednesday night, if all goes well, I should be streaming. We'll see if we can get somewhere with that. So thanks for watching, and yeah, I'll see you guys next stream.